So I make a sound check for the students at home. Can you hear me, guys? Can you hear me at home? Can the people at home hear me, please? Probably I don't get anything from. I'll try to do the sound check later on. It's not clear whether the people at home can hear me. Okay, I can. Okay. Thank you, Beatrice. Okay, I also want to check whether if you speak, if I can hear you. Can you say something, please? Can you unmute the microphone, say something, Beatrice, please?
Prof.
Ok, grazie Beatrice, ho sentito. Grazie. Salvatore.
Prof, le posso chiedere di spiegare un chiarimento?
Prego, ma collettivo?
Sì, vabbè, questo
ok, sì, facciamo collettivo.
Perché proprio il significato anche teorico, non so, spiegazione del perché nel GLS usiamo il peso quando dice le varianze e che significato ha il peso, perché poi ho visto, poi ho fatto male a cercare da solo magari su internet perché mi confondo di più, che c'è proprio un metodo di regressione che si chiama weighted
least square.
Esatto.
Di cui è un caso, è un caso particolare del GLS. Caso particolare del GLS, sì.
Però anche lì ci sono i pesi.
Sì.
Il peso che noi abbiamo incontrato comunque diventa pian piano più piccolo a crescere la varianza.
Esattamente, più è grande la variabilità, più, come dire, uno fratto la variabilità, do peso, uno fratto, quindi come dire, gli do praticamente, più grande la variabilità, più cerco, come dire, di dare un peso minore, invece più piccola la variabilità, gli do un peso maggiore.
Okay.
Questa è l'intuizione. Comunque adesso ci torno.
E poi dopo nel prep, perché dobbiamo fare una presentazione per il prep, io devo presentare la parte sulla parte quantitativa, devo chiedere una cosa di quel paper, però una cosa particolare di quel metodo dopo.
Va bene, dopo vediamo, sì.
Io ce la prendo.
Do you prefer this camera or the other one, this one? This is for the student at home, of course. I try to change it. This is the one, the closest one. Have you any preferences at home?
Not really for me.
Yeah, I can hear you.
Yes, not really. I don't have any preferences. Maybe I don't know.
Okay. It's up to me. Then it's up to me. Okay. I show you the classroom in the meanwhile. So people is joining the class. I will start in 5 minutes. I go to get some water if I can. I don't think I can. Okay, recording. Okay. What is no? Marco, why have you written no?
No, it was about the position of the camera.
You don't like this?
No,
okay.
no. It was.
I can understand you. I can understand you. It's much better if you look at your friends. Can we do like this? Probably not. I don't know. Much better this one, right? Should be. Well, we can do like this. I will switch to the long camera, so this one. And now moving to Panopto. Okay, we can do like this. Since it works, so this is okay. Let me just center a little bit. Maybe something like this should work. Okay. Now I open Panopto for recording, and thank you to all students for this. I'm sorry for our class. Actually, I was actually ready even yesterday, but I decided that I didn't want to put some schizophrenia in today yes, tomorrow no. So I decided to stick to the program. And so if you recovery is today, and if I remember correctly, on Friday 11 in the afternoon. Okay, thank you. Before I start today, I know that typically you are worried about the exam. I want to just to show you something related to the exam. And I have also understood, I have received some email that make me think that I need to clarify again the exam rules. But I don't know today if I'm able today. So let me open Panopto. Okay, so JavaSpeak, so this is the right one. Let's say that is class of applied econometrics and I will leave it in Italian. I think it's should not be a major problem. So I think we can start. So thank you very much. Welcome to the class of applied econometrics of March 2. Okay, and I see how many people is connected. I see something like 20 students connected, and there is also an external student. Well, there must be some reason, but anyway, it's fine. It's not a problem for me. 20 people connected at home, and I see something like roughly 20 also in the classroom. So there is a drop in the number of students. I want to start today with the following file. Probably I have to do like this. What is PDF? Why is it? PDF is presented like a very strange thing. This. Okay, let me do like this then. Okay, this one is. It seems that I don't have the Acrobat reader. Oh, maybe like this. Let me open Acrobat Reader, and then I do open, I have many things on the desktop. I don't know why it shows up. Those are PDF file, but anyway, let me open this. This is an example of exam. This time, this year will be slightly different because I will. This is last year, part 1. This is my question to group number 28. So, for instance, the next week, what we have to do the next week is starting to think about groups of people who are doing the exam. So maybe Salvatore, if not a problem for you, you might send me. You work on an Excel file where you send me. Group 1 is Marco Rossi and Paolo Bianchi. Okay, group 2, group 3 is only Salvatore. Okay, something like I want to know all the teams, all because each team will receive something like this. For instance, this is a question that you have to write. Describe the generalized linear regression model, the efficient estimator of the parameters in this model, and then provide an example of a feasible GLS estimator. But this is last year, I typically change year by year. This is part 2 is Professor Panagonitis, so I can show you that, okay? Because I don't know if Professor Panagonitis will repeat, but my idea this year will be something like a general question, and then I'm thinking, but I still have to decide that, something more empirical, so probably a question that might be equal for all students, but I send you a data set and you have to address a problem also empirically. So something like, say, a theoretical question, more or less theoretical one, and a more empirical one. That should be the setup of my exam. And as I said, when we finish in our last class, imagine that when we are closing our part, I should have a file with to send to all the people, and then you have to send me back the assignment by, if I remember correctly, it should be 8 April. This is the rule. That is written on the exam rules that you find on Virtuale. So this should be the setup. One important thing is that, as I already told, let me go on that because I want to be clear. I want to be very, very clear. Virtuale.
So we have like 10 days.
Yes, which is too much. Which is definitely much, but too much. But okay. This is the way we go, and but I want to be very, very clear because I will not accept any complaint. So I want to be. Let me stress this very clearly. Let me go on risorse didattiche. Okay, all the time. Okay. So teach exam rules. Let me open this file so we read it together. Okay. I want to be okay. So this way for me, at least for part 1, part related to Professor Fanelli, okay, to myself, you can do this way only until, say, in the first call. Starting from the second call, July 5, my exam will be a written exam in the classroom. This will not be more difficult than the other one. I'm not going to penalize people who will give the exam on July 5 or August 28. It will be different, but it will not neither easier, neither more complicated. Is that clear, guys? Also to the people at home. Why do that? Because I've been reading very carefully the rules that UNIBO has given to us, and the rules are that until May 31, we should keep the hybrid way, And since I cannot say to the people here, I cannot say to these people, okay, you get the exam in the classroom, and the guys at home, you do the exam at home. I don't like the EOL stuff. I don't use it. So either you work by working on this kind of assignment, let me say, which apparently you say. So if you want to skip coming in the classroom, please, you have to give the exam you have to send me your project by April 8th. Otherwise, I will wait you in the classroom. Okay, this must be clear. And waiting you in the classroom does not mean that the exam will be more difficult. The exam will be different, but the level of difficulty will be the same. Everything will be calibrated. Any question? Okay, question from the audience, from the classroom was, how many people for group? At most 2. This is against my interest, because of course then you cannot assume that on the 9th of April you get your grade. Forget about that. I will need my time. There will be a tutor who is Antonio Marsi, who is this guy you find here, Antonio. Is the official, say, the didactic tutor of applied econometrics. He will be helping me in reading your works, blah, 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 okay? So we need some time. You will meet also Antonio when Professor Panagonitis will be teaching, okay? But at a given point, you will get a grade on my part, you will get a grade of part Panagonitis, and I will be in charge of computing the average. Okay, and the rules should be very clear because are written in this. And as I want to come back on that for the people who has done the exercise of the crash course of econometrics, I will give a positive value depending on the context, of course. For people who has not given the crash course of econometrics, they will not be penalized. Okay. Now, this has been recorded. Let me check whether it has been recording. So I think that now it should be 100%. Yes, it is recording. Clear. But please, if it is not, let me know, because it is very important. The very important thing is that I will come back to the, let me say, traditional exam since July 5. But of course, you should. Let me also stress this: in a master program like yours, I prefer working with making people developing projects. I like that. But this is, an introductory course. I cannot having you working on a project. We have to learn basic econometrics. That is the very important. My mission in this. Of course, which doesn't mean you can become a very good econometrician. I'm working on the basement. You can go to the roof. It's not my mission is building a very good basement such that you can go to the roof if you want. That is my task in this master program. Then, before moving on with our program, I want to clarify one point because I've been asking by one of the students in the classroom to clarify one concept. So I'll try to do that now. Okay. Do I have the slide? No. Okay. Open. I don't know why today this computer visualize PDF file like Chrome. Very, very strange, but doesn't matter. The important thing is that I can open slides. Okay, no, slides applied economics, this one. The question was the following. Let me go to the GLS estimator, generalized least square. When I say GLS, you should open, there should be a light in your mind that say, okay, it means that the big sigma matrix is not like this. Let me put full screen. So you should have a light in your mind that say, no, okay, if it says generalized, it means that the big sigma is not like this, because this is the case of the classic linear regression model, when we have same variance and correlation, okay? When we say generalized, linear regression model, we mean case 2, which is heteroscedasticity, for instance, zero correlation, or this is the opposite, where I have homoscedasticity, case 3, very rarely we find case 3 with cross-section data. This is typical of time series data, but I will discuss that later on. But case 3 is where we have homoscedasticity. You can see that on the main diagonal, we have the same variance, which is sigma square epsilon times 1, 1, 1. So on the main diagonal, you have the same element. But so we have homoscedasticity, but you can see that we don't have zero. We may have non-zero elements on the off-diagonal terms. So we have correlation, okay? And you can see that in this setup, in setup 3, correlation are, or say covariances, are modeled like this. Say, I take, say, the element sigma ij, like the product of this guy times this tau coefficient, okay? So the tau is kind of correlations between the epsilons. And finally, case number 4, which is the case where if you don't have an idea about your data, how to model heteroscedasticity or correlation, is the case where the big matrix sigma is full. So I have different elements on the main diagonal, so I have heteroscedasticity, and I have non-zero off-diagonal elements, which means, say, correlation. And this is the worst case from the point of view of estimation, because if we don't know sigma, we cannot compute the GLS estimator. Now I'm coming to the point raised by your colleague. What is the expression of the GLS estimator? It's given by this formula here, which is very similar to the OLS, but you find this inverse big sigma appearing here, okay? And we did the story. We said, if we don't know the big sigma, we cannot compute it, this estimator. But if we have an idea about how to model, say, heteroscedasticity, for instance, we can compute a feasible GLS. Now, the question of your friend is, how do we get this estimator? This estimator is obtained by the same, I mean, it's simply a generalization. That's why we call generalized least square of the OLS. What we do, how do we estimate beta by OLS? When we do OLS, we minimize, say, this is the distance between, say, the true dependent variable, the one we want to explain, minus the one predicted by my model. Imagine for the moment that there is no big sigma here, so identity, okay? So they would be multiplied by this guy, so you are minimizing the square, the sum of square errors, which are, the error is the distance between true and fitted, true and what your model says, okay? That is what you do by OLS. Now, what is the generalization here? The generalization is that we are giving, when we put into role, when we give a role to the big sigma matrix, in particular to the inverse of the big sigma, okay, we are giving also a role to the variances and covariances. Now, in order to understand the meaning of this expression here, simply think about case number 2. Case number 2 is the one, this one, I go back. Okay, this case number 2 is the one where we have heteroscedasticity, okay? Now, you should agree with me, it's not very difficult to envisage that if you take sigma inverse, it's simply, again, a diagonal matrix where in place of sigma square 1, I have 1 over sigma square 1. I have 1 over sigma square 2, blah, blah. So the big sigma inverse is given by, is again, a diagonal matrix with the inverse of the element on the main diagonal, okay? So keep in mind this, if it is true. Now, let me come back on the minimization problem we solved with the GLS, which is this one. Now, in that case, you should agree that, so I'm calling, just for simplicity, I'm calling psi ij the elements on this matrix, okay? And you should recognize that since the big sigma now is diagonal, when I is different from j, this guy is equal to 0. Okay? This guy is different from 0 only when I is equal to j. Okay? And this psi is equal to the inverse. For instance, let me consider psi 1, 1, okay? Psi 1, 1 will be 1 over sigma square 1. It will be the opposite of the variance of the error term first unit. So you understand that we are giving away, we are weighting the distance between actual and fitted, and the weight we are giving is just the inverse of the variance. So the larger the variance, the less will be the weight. So if we have big distances, we are giving less weight. If we have small differences, we try to give him more weight. So we try to balance. And that is with the OLS, you don't balance anything. Any error will have the same weight. Now we are giving weights. And that's the end of the story. Why do we give weights? Because it is possible to prove, as we have been discussing that quite easily, that this estimator, if you know the big sigma, this will be more efficient than the OLS estimator. So you get better standard errors. So and we saw also so if I take standard errors from this matrix, it is much better than taking from the OLS. That is the advantage of giving weights. And you can see that the weights also enter the standard errors. Is it okay? Did I clarify? Simply, we're simply giving some weights to the errors, and that's it. Okay. And as in our last class, maybe, or the previous one, we saw an example in which we can, for instance, we can make a guess about, say, the heteroscedasticity. Think about the example. I will come back today on that example when we estimated linear approximation of the Kuznets curve for 11,000 blah blah Italian households. Okay, and in that case we made an hypothesis about the heteroscedasticity, and we have been able to computing a feasible GLS. And I show you that is similar to transforming your model, and you can go alternative way is doing OLS. But this is one of our last classes, so I don't want to come back on that. Okay?
So does it mean that our estimator is less influenced by the outliers elements?
Very good point. Yeah. The point raised from the class is that, so when doing this GLS, we are giving, is it a way of, imagine that, say, we are weighting, as you said, giving a weight to the error. So if I have a large error, I'm giving less weight to it. So it's a way of balancing, say, big errors and the small errors. And that's it. Okay? Now, let me let me open. I want to make the point where we are, our program. This is the file, should be this. Oh, sorry. Where is it? Program, okay, this one. I want to show you that we are working now, we have been working very quickly. This is where we are. Now, today, I'm moving to studying test of hypothesis in the linear regression model. I know that 0.5, the properties of OLS estimator could be perceived as boring for the classroom. I understand that, but you will see that 5 and 6 are strictly connected. Not in the sense of being both boring, but in the sense that I needed to give you some flavor about properties of OLS estimator. Otherwise, you don't understand why, when you have to test an hypothesis, why you should look at the ratio, the f-test, chi-square. I'm working on give you the ingredients to understand. That is I don't want you to do many things. I want you to understand the very few things you do, but you have to understand that very, very well, as econometricians do. Not like applied people. There is a difference from my point of view. Applied people, anyone can be an applied people, anyone. But applied people tend to make mistakes because they move on mechanically. Econometrician use their mind. They must understand the problem, okay? Now, I'm moving to 6, testing hypotheses and confidence intervals. We'll discuss confidence at the end. Now, the important thing, I want you to get familiar with testing hypotheses in the linear regression model, okay? And this is exactly where I'm moving now.
Professor,
yes?
I want to ask that if we are in a trap of correlation.
If you are, can you repeat, please? Sorry.
We are in a situation where the regressors are correlated.
Correlated each other, okay?
Should we take care of correlation problem?
Okay, this is one question by the classroom was, okay, what about, let me show the model. Okay, this is a very nice point to at least to discuss with you. And let me go back in order to address your point. Let me go here, okay? OLS estimator. The question from the audience is, okay, what if we have correlations? I have my model where I try to explain my dependent variable by using some explanatory variables, some regressors, and we know that when we do that, we are in a, we are doing kind of experiment. We are implicitly assuming that causality runs from the regressors to the dependent variable, and we say that is consistent with interpreting the linear regression model as model for the conditional expectation. We condition, say, the variable we want to explain upon the x's, okay? Now, the point is, if the x's are correlated, I mean, we don't need to condition with respect to all the x's. We simply must consider the relevant ones. So if they are redundant, we can keep some x's outside the problem. So there is a big difference in the way statisticians treat this problem and the way econometricians treat the problem. When statisticians have regressors which are very highly correlated, they call it, say, multicollinearity. And they have some special methods to address that. What is multicollinearity in practice? You know that in order to compute this matrix, this estimator, sorry, you need the X, you need, say, the big X matrix as K columns, okay, which are observations on the K regressors. Now, the columns of the X matrix should be linearly independent, which means the information provided by regressor 1 is not already contained in the information given by regressor 2, given by regressor 3, and so on. That is the meaning of having this matrix of full column rank K. It means that the K regressors are not redundant, okay? And if they are not, you can invert this matrix. Otherwise, if you are in a situation in which one regressor is almost a linear combination of the others, it will be very difficult to compute this object here, because this matrix here will not be invertible. So the question by your colleague is, how do we address these problems? So as I said, statisticians use techniques to address multicollinearity. But if you think about the problem, if you think about seriously the problem, you can do transformation. What is a regression model? It's simply an equation. It's an algebraic equation. And the algebra says, okay, guys, what you can do on the left, if you do something, if you add something on the left, you also have to add something on the right. If you multiply something on the left-hand side, you have to do the same on the right-hand side. That is linear algebra, okay? Those are the very basic principles of linear algebra. And using this very simple principle, you can rewrite the same model. You can manipulate a little bit the model such that if you are intelligent, if you are an expert of the problem, if you are aware of what is going on in your phenomenon. So that's why all the time I repeat, I stress that you should be an expert of the problem you are dealing with, okay? And that is sometimes a problem on statisticians. Statisticians, they think that, okay, I have a method, I know the methods, I can do whatever I want. No, that is not the way to go. If I'm modeling, say, COVID, I should be an expert of COVID. I should know what is, say, I should at least have the basic ingredients of epidemiology, blah, blah, blah. And I have to say that after the outbreak of the COVID pandemic, I saw so many, the day after, I saw hundreds of papers of colleagues working on, how to do the COVID. I'm not joking. I really saw, say, I said, I was probably the only econometrician not doing anything about COVID after the pandemic, because I understand that we want to do something, but yes, we have to be careful. And you know that we have been listening everything about COVID. I've been heard almost everything. And I'm quite sure that we are only partially understood how COVID works, okay? But anyway, this is just, I'm joking, of course. So the point is, statisticians apply methods that address that these metrics might not be full column rank. Econometricians, what they do, they think about the phenomenon and try to kill the column, the regressor, which is explained by the other one. So they manipulate the model such that the collinearity you have in the, say, you can manipulate the model such that the linear columns of these metrics at the end of the day are linearly independent. I understand now that what I'm saying can seem tricky, can be kind of magic, but it is not. I will try to present you an example, if I can, where it is possible to address the problem. Okay.
But if we kill one of the regressors, but we think that the coefficient of correlation.
But I'm not saying that you simply kill one of the regressor. I have to stop you. I'm not saying that you simply kill one of the regressor. I said that you rewrite the model such that, say, this collinearity disappears.
Otherwise, the model is misspecified.
Otherwise, the model has you have some redundant regressor. I don't know whether it is misspecified or not. It's a term that can be abused, but yeah, I understand what you mean. But I will try to think about an example where you can manipulate the model in algebraic way such that you solve the collinearity problem. Okay, but we don't have the time, unfortunately, to cover that. But thank you for your question. Any other question, clarification, guys? Oh, I like very much this interaction. Are precious to me. Okay, let me go to point 6, testing linear hypothesis. Okay, and this is very, very important topic because if you do that, if you realize that you test mechanically, it means that no, that is not the right way to go. You have to understand what happens. So what we do, testing hypothesis and confidence interval are roughly the same thing, but I will discuss testing hypothesis first, and then we'll move. If you have understood testing hypothesis, you will realize that computing confidence interval for the coefficients, it's very simple. Okay, so testing hypothesis, we have in mind the classic linear regression model that now you know very, very well. We have the OLS estimator of beta that we know very, very well, and we have the OLS estimator of the sigma square epsilon, okay, that we know also very, very well. Those are, please let me recall that these guys here, when you compute sigma square epsilon, this is the sum of square residuals. Residuals are when you have beta hat, errors when you have beta that you don't know. So errors are a logical experiment, they do not exist in practice. We don't observe, we know there is the error, but we don't see the error. We do errors, but we realize after estimation that we have the errors because we quantify the errors by the residuals, okay? Now, after the model is estimated, so after we have the column beta at in Stata or in Gretel or any package you are using, we are interested in testing linear hypothesis on the beta. on the population parameter. And now I'm providing you with some examples, okay? We have both economic and statistical reasons for testing restrictions on the parameters, okay? And I'm going to show you 3 examples that show that we typically are interested in testing either single coefficients, single elements of the beta vector, or sometimes we are also interested in multiple elements. We want to test jointly whether, say, one parameter is equal to something, the other parameter is equal to something, and so on. So we can make single statement, but also multiple statements, okay? But the best thing to do is to consider a set of examples. So example 1, we already been discussing this example. Imagine that I'm modeling, so I have one country, Italy, and this is the CO2 emission of Italy at time t. I think you will be dealing with this model with Professor Panagonitis, if I remember very well. But imagine this is our model. So CO2 emission depends, okay, we have an intercept on real GDP, okay, and we have CO2 emission in the previous period. Plus, any questions? Question at Tom? Okay, no. Plus error term, okay? Now we estimate, so which are the parameters in this model? Are the beta are beta 1, beta 2, and beta 3. In particular, we are particularly concerned with beta 2. We capture, say, of course, let me say one thing. Let me come back on this issue. I'm modeling log of CO2 emission and log of real GDP. So by modeling logs, this beta 2 will be the elasticity of CO2 emission with respect to income, okay, with respect to real economic activity. The interpretation of the parameters is easier. And when you estimate your model, you see that the estimated coefficient you see are something like 10,000, blah, blah, blah. Say, stop it, and make one step behind. I don't want to see coefficient, say, very, very large coefficient, very, very large standard error, even if the T ratio is good one, but that is a sign that you are not modeling the right way your data. Do log transformation when you can, and that will simplify the interpretation of your coefficient. So, beta 2 coefficient, now, it will be very important testing. Then in this model, the crucial hypothesis to test will be testing then the null hypothesis that we write like H naught, that beta 2 is equal to 0, which implies GDP does not affect CO2 emission. It would be, let me call it the Trump hypothesis. People who deny that there is any connection between, say real economic activity and gas emissions. It seems strange to you, but it's plenty of people that would say that H naught is the right hypothesis. There is no connection. Of course, I'm a student of this master program. I imagine that you would, you would bet on H1, which is, say, beta 2 is in the population is larger than 0. So GDP, real GDP affects the emission, CO2 emission. Okay? And this is an hypothesis you can see on a single coefficient. And if you think about the information we have so far up to this point, if we run this regression model, we get from Stada or Gretel. I will talk about Gretel since we are working Gretel. You will get the column of estimated coefficients. So you have B1 hat, B2 hat, B3 hat. You have the column of standard errors, and we know that they quantify, say, the variability of the estimated coefficient, and we know now the column of T ratio. Now we're moving, I'll show you that, say, we can test this hypothesis by looking at the column of T ratio and also the column P value that you find nearby the column T ratio, okay? This is what we want to learn today. So, testing H naught B2 equal to 0 amount to test the significance of a single regression, okay? And as the slides say, the simplest way to go in this case is to consider the T-ratio test, but we'll see that, okay? But in alternative, I will discuss with you a more general approach, which covers, say, the T-ratio as a special case. The T-ratio will be a special case of the more general approach we are going to consider, okay? Example number 2. Let me consider the same model as before, but I must say, okay, before testing, say, I could be interested in testing whether the model I have estimated is good or not. And for instance, so I could be interested in testing the null hypothesis that jointly beta 2 is equal to 0 and beta 3 is equal to 0. Let me go back. The model is this. If beta 2 is equal to 0 and beta 3 is equal to 0, it means in your model that CO2 emission is simply a constant plus error term. So it's something that says CO2 emission is kind of the quantity of gas emission you find in the air, you measure in the air, is kind of random. Does not depend on anything. Okay? So in this case, in this second example, I want to test jointly the null that both coefficients are equal to 0, which means both regressors are not relevant. Both real economic activity and the CO2 emission in the previous period are not important, not relevant to explain CO2 emission today. Okay? And of course, which is the alternative in this case will be at least one between beta 2 and beta 3, at least one of the two. So they could be both. At least one of the two is different from 0. And when you have the Gretel or Stata output, you have the F test in the standard output, and the F test will be a test for an hypothesis like this. So you can regard it as a testing the overall validity of the estimated model. Okay. The slide just repeat what I said in words to you. Okay, example number 3. Okay, imagine, have you ever heard about, say, a production function? What is a production function? It's very, very simple. Imagine that you are thinking about, say, the manufacturing sector. Okay, and sorry, just one second. Also, we are talking about the manufacturing sector, and a production function is a model. You can think about a model that say what you produce in the. Imagine that we have a number n of. So in this case, I'm considering a cross section as example based on cross section data, and imagine that the model said, okay, the production of firm I, okay, in my sector, the manufacturing sector, depends, okay, on a constant, on the input, the quantity of labor. So again, you can see when I define the variable log of production. So yi is the log of production, or from a practical point of view, could be the value added of the firm. Okay. What is lab I? Lab I is the log of employees, people employed in the firm. Okay. And with cap I call the log of the stock of capital used by firm I. And so you have to think about a production function, something like I have inputs of production, labor and capital, and in response I have production up to error term. Okay. Now, what is the typical assumption we might be interested in testing in this model? The typical assumption is that the sum of beta 2 plus beta 3, the sum of this coefficient plus this one, is equal to 1. And economists, industrial organization economists call this assumption constant returns of scale. I don't want to enter this theory. It's just an assumption we might be interested in testing. And you can see this assumption involves, say, the sum of this coefficient. The sum of beta 2 plus beta 3 must be equal to value 1. The alternative in this case could be different from 1. For instance, if the sum beta 2 plus beta 3 is larger than 1, economists call that increasing return on scale. But if you are not an economist, if you come from engineering, blah, blah, doesn't matter. The important thing is to understand that we are interested in this example in testing whether the sum, the linear combination of coefficients is equal to something, okay, or not. Economists, when the sum of beta 2 plus beta 3 is less than 1, they say that the sector is, manufacturing sector is working under decreasing return on scale, which means, what is the idea that of constant return on scale? It means that if you had, say, 0.3 of labor and 0.7 of capital, so you are increasing your input, your production will increase of 1. But if you have increasing return on scale, imagine that you increase labor of 0.3, you increase capital 0.7, and you get in response 1.5. So you basically, your production is larger than the inputs you are giving to the economy. Okay? And the opposite when the sum of the two coefficients is less than 1. So in this case, the null hypothesis involves a linear combination of the element of beta, because beta 2 plus beta 3, as Professor Dieci would say to you, this is simply a linear combination of beta 2 and beta 3. Okay? In this case, it will not be convenient using T-ratio test, but it will be convenient using something different. Okay? Something like an F test. Okay? So, everything clear now? Still 5 minutes, then we'll make the first break, okay? Still give me 5 minutes. Any question, clarification, guys? Okay. Now, what I'm doing now, I want to show you that all the 3 examples we have seen are special cases of a more general formulation of linear hypothesis on the beta coefficients. And once we understand this general formulation, we cover everything. So we don't have to think, oh, let me take the manual, what is this case? No, we have just one case, very general one, which covers everything, okay? And this general formulation is like this. So we have the beta vector, and imagine that we have a number q. So a beta vector contains k elements, as we know, k regressors, including the intercept, the constant, okay? Imagine that I'm considering a number q, where q is less than or equal to k, linear hypothesis on the parameters beta, and this linear hypothesis can be written in general form in the following way, that now I understand that you might say, this is a very, what is this stuff? I don't understand it, but now I'm coming back to the 3 examples, and you will see what is this big R and the small r, okay? So a very general way of writing Q linear restrictions on the beta parameters is writing H naught like this. So we have big R, beta is equal to small r. So what is big R and what is small r, okay? So big R is a matrix which has Q rows, where recall that Q is the number of restrictions, constraints we want to test, okay? So the R matrix is a matrix which has Q rows, and each row contains 1 and zeros. But now you will see in practice the example, okay? What is small r? Small r is a vector which also has a Q rows, and you will see that it allows to manage the restrictions. But now it will be clear with examples, okay? Of course, this is the null hypothesis we want to test. The alternative will be that the null is not true. So I'm writing capital R beta is different from small r. Let me show you an example on case 1, example 1, and then we make the break, okay? So example 1 was the model about CO2 emission, this model here. CO2 emission time t depends on constant, GDP, real economic activity at time t, and CO2 emission at time t minus 1 plus error, okay? We said we are interested in testing that the coefficient beta 2 is equal to 0. This is the Trump hypothesis. There is no impact of real economic activity on CO2 emission. Okay? So what is, in this case, you should agree with me, you should realize that we are considering just one restriction. So Q is equal to 1. Okay? And the big R matrix does the following job. I have 0, 1, 0. So if you do this row times this column, you get exactly beta 2 will be equal, what is small r on the right? It's simply 0. So I have written this beta 2 is equal to 0 in this way. And you will say, why are you complicating my life? I don't want to complicate your life. I want to simplify it. And you will see that later on. So you have to pay a little price now, but the reward will be very, very high. And you know that in order to get high rewards, you have to also pay high prices. Okay? So for the moment, I stop here. We take, it's 4 o'clock. We take, say, 15-minute break. Okay? We start at 4:15.
Scusi, professore, avrei una
Prego.
domanda.
Sì, prego.
Allora, mi è sfuggito perché la matrice moltiplicativa R è data da 0, 1, 0. Cioè, noi sappiamo che il numero di righe è 1 perché è pari a Q. E perché abbiamo 3 colonne, scusi?
Colonne perché il beta, allora, torniamo qui.
Ah, ok, il numero dei parametri. Okay.
Beta è il numero dei parametri, quindi beta è fatto così a 1, 2, 3, beta 1, beta 2, beta 3, e quindi sto prendendo una combinazione lineare di beta.
Ok, perfetto, grazie.
Prego. can't see the blackboard. Can you see this, Satan? I don't think they can.
Not really.
Not really. Okay, not really. But I can do like this. No, this is no. I cannot move this. Okay. The next break, I will show you one way to deal with multicollinearity. Okay, on the blackboard. Okay. Before I move on, since I like also very much anecdotes in order to break a little bit, say, monotony, let me show you this guy. Then you will understand why. Okay, of course. Okay, no, in English. Okay, this one. Okay, this guy, Abram Wald, was an Hungarian mathematician, Jewish mathematician, who contributed to decision theory, geometry, and econometrics. That's why I know him, okay? And you will see at a given point that, let me just, since we are in war times, he has given an important contribution during the World War II. Basically, I've been studying the damage, the way to protect the Royal Air Force when they bombed, say, Germany in aircraft wars. He developed, say, something which is known today like survival analysis. But why do I am, say, I'm talking about the world? Because today we are talking about what in econometrics are known as world tests. The tests we are discussing today belong to this man. Okay, that's why we call the world. When you hear world test, we are. Let me see if there is something about the world test. Okay. Anyway, it will be, his name is related to testing, the test we are doing just now. Okay. So why are we discussing this general way of writing linear restrictions on the parameters beta? Because at the end of the day, what we'll do, we're going to run world type test for this null hypothesis, okay? But I will we'll see that later on. So example 1, Q, we have just one restriction, so we have just one row of the R matrix. This row simply have to pick out the beta 2 coefficient from the beta vector and put it equal to 0. Now let's move to example number 2. Example number 2, we wanted to test that jointly beta 2 is equal to 0, and that's why I have included and. There is an addition. Beta 3 is equal to 0. So now you understand that we are considering two linear restrictions on beta, because we want to kill beta 2 and we want to kill beta 3. So you understand that the capital big R matrix now has two rows, and the first row has to select, say, beta 2. So I have 0, 1, 0. I'm selecting beta 2, I put it equal to 0. And the second row will select beta 3, so 0, 0, 1, times beta 3, I get beta 3, and I put it equal to 0. So big R is a matrix with two rows and three columns. the two rows must be linearly independent, otherwise I'm putting restrictions which are linear dependent, does not make sense. And small r is a 2x1 vector containing 0 and 0. Thank you. If you can close the door, thank you very much. Thank you very much. Can you close it? Okay, wonderful. And so this is, again, we have to say, this second case is still written in the general form capital R beta small r, okay? Questions? Example number 3. It was our production function, and we wanted to test that beta 2 plus beta 3 is equal to 1, a constant return of scale, okay, in this sector. And you understand now that we are putting one restriction, Q is equal to 1, because we are saying that the sum of these two coefficients is equal to 1. And what about the capital R matrix? You understand now that if, say, there will be just one row because Q is equal to 1, and if I do this row time this column, I'm simply summing beta 2 plus beta 3 equal, on the right hand side, I'm putting 1. Any linear restriction can be represented in this general form here. So all the linear restriction we are interested in can be represented in this way, given a specification of the big R and a specification of the small r. And so our mission now will be developing a test for this general H0 versus H1. Okay? So, what the slide says, since we can represent any linear hypothesis on beta in general form, our objective will be discussing a theory for a testing problem like this. Okay? And we are doing that in the classic linear regression model. I could do in the generalized one, but I mean, it would be simply an exercise to do after having understood what we do with the classic linear regression model. Okay? And you will see that the T-ratio test will be a special case of this. So, roadmap, what we'll do now. In the next slides, the roadmap will be this one. First, we will find a short summary of the statistical theory of tests. Okay? I'm providing you simply with the main concepts. Okay? Then we'll move to theory of tests on single coefficients. So when we have something like beta 2 is equal to 0, or if you prefer it, say it is the theory of T-ratio test. Okay? We will test single coefficients by the T-ratio. And we know that the T-ratio for the moment is something given by, in the numerator I have the estimated coefficient, in the denominator I have the associated standard error, which is a measure of variability. Okay? And finally, we move to a general theory for the very general special case. Okay? So general linear hypothesis. Okay, summary of statistical theory of tests, because you have to know what we are talking about. As you have understood that I don't want you to know things mechanically. Okay. So what is a test? A test is a part of inference process. What is inference? Inference is basically the process by which we observe, given some observation, some data, we attempt to make claim about the population that we think has generated the data. That is inference. And in order to do that, we can do that only by using probability. We cannot make a 100% sure claim. We will do mistake, and our objective will be controlling the mistake we do. That is what we do when we test hypotheses. So a testing problem requires solving a probabilistic decision rule by which given the data, given the observation, we have to decide whether we have to favor H0 or H1. So given the data, given a decision rule, we have to decide whether we support H0 or we reject H0 in favor of H1. Okay? Since it is a probabilistic rule, no certainty, we make mistakes. And the idea is to decide between H0 and H1 by keeping possible mistakes under control in a probabilistic sense. This is what we want to do when we test hypotheses. So we need three main ingredients when we test hypotheses. A, we already know A. We need the null, which is the statement about a population value that we want to control for, okay? And of course, we need an alternative, H1, okay? B, we need what we call a test statistic. When we talk about test, we are using a random, a test statistic will be a random variable at the end of the day. That's why it is important to know at least the basic ingredients about random variables. The test will be a random variable. It will be distributed like a normal, like a student t, like a chi-square, like an f. That's why we have to know distributions. And C, the last ingredient will be what is the probabilistic decision rule? How do we decide whether supporting or rejecting H0? And now what I'll do, I'm going to examine all three ingredients one at a time. But we already know A, okay, the null and the alternative, so I will be very fast here. The null hypothesis, we are seeing it's just statement about population value of the parameters. We are seeing three possible examples. So A will be I'll be very, very fast on that. B, this is very interesting. A test statistic. What is a test statistic? A test statistic will be a function of the data. It will be typically a function of our estimators, and that's why I have to bother you with the properties of the OLS estimator, because now it is related. The property of the OLS estimator will be to some extent inherited by the test statistic we have to consider. Now we are building a puzzle. We have a puzzle, and we have to know all the pieces of the puzzle. Otherwise, we are lost. Okay. So let me show you an example. In the linear regression model, we denote. I will use the following notation for test statistic. I use S just to say statistic. I'm going to use N to recall you that we have a sample of small n observations. And for instance, our test statistic will be a function of beta hat and sigma square hat. Beta hat, the OLS estimator, and the OLS estimator sigma square epsilon. For instance, we see that when we want to test the Trump hypothesis versus, say, can I say the Greta Thunberg hypothesis, H1, okay? We are going to use the t-ratio. The t-ratio is, our test statistic will be the ratio between the estimated coefficient beta 2 over the standard error of beta 2, which is given by the estimate of sigma square epsilon, not square, sorry, sigma at epsilon, okay? C22, what is C22? Was the square root of the second element on the main diagonal of the x prime x inverse matrix. Just come back on the standard error, you will find that this guy here is the standard error of beta 2 hat. And you can see this is a test statistic because it is a function of the estimators, and the estimator are a function of the data. So this is a random variable with a given distribution. Okay, so test statistic is simply a function of the data. And in particular, it is a function, more precisely, of the estimators we deal with. You can see that in this case, the t-ratio, I have beta 2 hat on the numerator, and I have the standard, the associated standard error on the denominator. Now, what is crucial about a test statistic? It is very important that we know how the test statistic is distributed under the null. And of course, it will be also important to know the distribution under the alternative, but you will see that we focus especially on how the test statistic is distributed under our null, under H naught. Let me give you again an example, okay? Imagine that we are dealing, and now it is very important that you know, you have in mind, say, what we said in our last class about the properties of the LS estimator. Do you remember we divided small samples and large sample theory? Now it will be crucial having that in mind. Why? Imagine that we are dealing with a small sample, okay? So n is small, but in that case, we said that in order to know the distribution of our estimator, we need to make an assumption about the errors. For instance, we have to assume that the epsilon, the errors, conditioning on x is normal, okay? It's very convenient assumption. Not always satisfied by the data, but it is convenient from a mathematical, statistical point of view, okay? So under this assumption, given this, and given that n is small, it's possible to prove that the t-ratio, recall that the ratio was the ratio between beta 2 and its standard error. Okay, this random variable here, under the null, so if the population parameter is equal to 0, is distributed as a student t with n minus k degree of freedom. I don't want to prove it. I don't know if I have the proof of that. Probably not. I skipped that. But it's possible to do that. I need some extra hours. But let me, please, believe me that it is possible to prove that. If you have normality in the error term and n is small, the t-ratio, if the null is true, is student t. And now I want to give you just the I want to anticipate the intuition. What do I do? Why do I need, I mean, what is the use I'm making of this information? The use is the following. Imagine that, say, okay, if under the null, I know that this t-ratio is distributed like a student t, and let me plot again the density function of a student t distribution. It's very similar to the Gaussian, to the normal. Everybody knows the normal. Before the euro in Germany, there was the currency was the mark, and I still have a 10 mark, and on the 10 mark you will find the face of Gauss, mathematician Friedrich Gauss, and there is also the Gaussian. It is plotted on the mark, on the 10 mark. I don't know if I have it with me, but I gave it to my son, but you know, they said, okay, I don't need marks, we have euros, so. And anyway, so why is it, let me plot you the student t. Imagine that you have the student t distribution, okay? And let me plot it to you. It's normal f chi-square. Have to, okay, student t. Okay, imagine that the point is, I have the example of a student with 3 degrees of freedom in this simple example. And I know that if beta 2, if the Trump hypothesis is true, under the Trump hypothesis, my t-ratio has the following distribution, okay? You can see that the student t, the density is very similar to the Gaussian, but it is a fatter tail, a larger tail, which means that rare events on the tail have more probability to occur relative to the normal, okay? Now, imagine that I know that if the beta 2 is equal to 0, if the Trump hypothesis is true, then the t-ratio is distributed like this. And in my sample, from Gretel or from Stata, I observe a value of the T ratio which is very, very, very large, which is very, very in the tail. So the idea is, if it is located in the tail, it is a very low probability to occur. One thing, if I have the T ratio is around here, you can see that the probability to occur is very large. But if I have one value which is located in the tail, it means that it is less likely to occur, okay? So, if I know intuition, I know that if the Trump hypothesis is true, then the T ratio is distributed like this, okay? If in my sample I observe a value, the T ratio, which has quite large probability to occur, I believe to the null hypothesis. But on the other hand, if I see that my T ratio has a very low probability to occur, I no longer believe to the null hypothesis. So I will reject it. This is the way we think. And the question will be, so which is the cutoff value? Which is the value, I mean, when the T ratio is large such that we reject the null, and when the T ratio is small such that it has a large probability to occur and we don't reject it. And in order to decide which is the cutoff value, we need an additional ingredient. And we have to move to the probabilistic decision rule. Okay? Is it clear, guys, what I'm saying up to this point? I come back to the slide. No, sorry, the slide are here. So, I said, the crucial information we have to know about a test statistic is the distribution of the test statistic under the null. And for instance, in this example, if n is small and you have normality, you know that the T ratio, if the null is true, is student T with n minus k degree of freedom. So the intuition is that if I observe a very large value of the T ratio, which is located on the tails of the distribution, I'm a little bit skeptical about the null. Otherwise, if I observe a value of the test statistic which has high probability to occur, I tend to believe to the null hypothesis. So I will accept it. So I'm coming now to the decision rule. The decision rule will give us the cutoff point. When the T ratio is large and when the T ratio is sufficiently small. Okay? So decision rule, it is the probabilistic rule by which we decide whether to reject or accept the null hypothesis. Okay? And there are two equivalent ways through which we can decide whether to reject or accept the null. Okay? The first is the decision rule based on the critical value of the test, and the second, there are just two alternative ways to go. Let me say the second is the decision rule based on the p-value of the test. Please recall, for instance, that you have all the time you have a test in your package in Stata or Gretel, you will find a p-value with it. So you can immediately recognize that the way statistical software econometric packages go is the second way. The packages provide us with the decision rule based on the p-value of the test. The decision rule based on the critical value of the test is something which is in our mind. Okay? So software is going to simplify our life. When I was roughly your age, I don't have, we just have a very rudimental software for doing regression, things like that. We're used to, we have no p-values. You will see the p-value is simply an area. Let me go back to a p-value will be something like this area here, and you have done calculus with Professor Diaz, you know this is kind of an integral, okay? And today, any package can compute an integral numerically, so it's very easy to provide this number, a p-value. During the first 90s, when we had the first softwares for packages for statistical econometric analysis, you simply add the test statistic, and you have to go with the decision rule based on, not on the p-value, but on what I call in my slide, let me go full screen again, the decision rule based on the critical value of the test. So I want you to do both. If you understand one, you also understand the other, and vice versa, okay? So decision rule based on the critical value of the test, C1, okay? The decision rule is something like this. We reject the null if, say, the typical rule is if the absolute value of the test statistic, say, for instance, the absolute value of the t-ratio, is larger than a critical value, CV alpha, where what is alpha, the critical value, which is also known as cutoff value or threshold of the test, is something which depends on alpha. And what is alpha? Alpha is the level of significance of the test. And this alpha is provided by us, by the tester. Before running the test, we decide the alpha, and you will see that we're going to decide where to locate the cutoff. So it is up to us deciding which is the cutoff value for accepting or rejecting, or if you prefer, rejecting or accepting the null. Okay? In particular, more precisely, CV alpha is a quantile or percentile taken from the distribution of the test statistic under the null hypothesis. Let me go back. Come back to we said the t-ratio, when n is small and we have normal distribution on top of it, n is small, we know that this ratio under the null is distributed as a student t, okay? Now you understand that the alpha is simply a quantile, will be a quantile of the student t distribution. And we don't have to know the quantiles of the student t distribution. They are published. When I was young, they were published on, you know, you have your book of statistical econometrics, and at the end of the book, you have the tables of the student t, tables of the chi-square distribution, tables of the f. Today, we don't need tables because the software gives us p-value. I will see the other way to go. But before moving to the other way to go, I want you to understand this way to go, the traditional way to go, based on, you know, where we have to know, where you need to know something about, say, percentiles of distribution. For instance, let me come back again on the student t graph, okay? This number here, 3.182, is a percentile of the student t distribution with 3 degrees of freedom. And in particular, what is a percentile? We know that if I take 3.182 here, and I take the student t is symmetric exactly as the normal distribution, okay? And you take minus 3 on the left, okay? This area, the one I colored like this, plus this area, the sum of these two guys is 5%. So this quantile, so the probability that, say, let me call S the random variable which is distributed at a student t with 3 degrees of freedom. So the probability that a student t with 3 degrees of freedom takes value equal to 3.182 or larger than 1.82 is 25%. On the other hand, the probability that S is less than minus 1.182 is 2.5%. So you understand that the probability that absolute value of S is larger than 3.183 is 5%. So this will be if you are running 3.18 is, say, a percentile, a quantile, or percentile, it depends on, it's up to you how to call it, of the student distribution with 3 degrees of freedom. And why do we need it? We need it because, let me go again, full screen. Because, I mean, this CV alpha is exactly that number. And why change? I mean, if I prefix the test to the level 10%, not 5%, I want to test at the 10%, what does it change? Why this value change? Yes, it will change because you understand that now, if I want this area plus this area to be 10%, you understand that the critical value will be something here. And you understand that with this rule, with this decision rule, we said you reject the null if the T ratio is larger than the critical value. You understand now that if you are running a test where the T ratio is distributed with a student T with 3 degrees of freedom, we reject the null if we find that the T ratio is larger than 3.18. So if we have a T ratio which is here, or here, of course, because I had absolute value, okay, then we reject the null. Otherwise, imagine that in my sample, the T ratio is equal to 1 point something, which is here, I accept the null. If I get a T ratio which is 5, so it's something which is here, I reject the null. And you understand that depending on the probability on the alpha, and now we'll discuss the alpha. Depending on the alpha you prefix before running the test, you will decide how large or small is the rejection area or the acceptance area of the test. It's up to you, up to the user. And now I want to reflect a little bit about the meaning of this cutoff value and this probability here. Okay? So the quantity CV alpha is a quantile or percentile taken from the distribution of the test statistic under the null hypothesis. Then we'll move to Gretel. So we'll see also the empirical things. In order to determine the value of C alpha, the investigator must prefix. So before running the test, we should say alpha is equal to 5%. That is the typical choice people do. But alpha could be 1%, alpha could be 10%. Alpha could be very, very recently, for instance, in the question is why do people just an example, if you're working on fiscal multipliers, something that I do in my research activity, for some strange reason that I don't understand, people use the alpha equal to 32%. Why? Of course, you understand that you know the larger is the alpha, the shorter will be H naught, the area where you accept the null. If you fix the alpha to 1%, so the cutoff value will be larger than 3.18, will be 4 something, because you are looking for a probability which is 1% in the tails. You know that for the moment you are skeptical, a little bit perplexed about what I'm saying, but everything will be clear. Don't worry about that. Now, to determine the value of the critical value of the test, the investigator must prefix this value. And now I want to explain you what is the meaning of this alpha level, which is crucial to determine, say, the cutoff value. So it's crucial to determine whether we accept or reject the null. Okay? I want to explain that another example. Let me, again, example number 1, which was the Trump hypothesis, beta 2 is equal to 0. Imagine that we are dealing with, we know that, imagine that you are dealing with a small sample, so n is small, we know that in order, when we are dealing with small sample, we know we need an assumption about the distribution of the error term, and the typical assumption we make is normality, okay? Now, imagine that n minus k is equal to 7. I'm just taking an example, okay? It's just a number. Then, we know that under the null, the t ratio, so the ratio between the estimated coefficient over the standard error, this t ratio, is distributed under the null as a student t with 7 degrees of freedom. Then, how do we decide whether to reject or not? Then, if I prefix alpha to 5%, and we call this alpha level of significance, the decision rule will be, I'm just following mechanically the slide for the moment. The rule is reject the null if your t ratio is larger than 2.36. And now, what is this 2.36? This is the CV, the critical value at the 5% level. If you go on the table, if you take a table of the student t, you do not have to know this number, of course. Well, how did I get this number? I went to the table of the student t distribution with 7 degrees of freedom and said, okay, which is the critical value? Let me check it. Let's do it together with Google. I hope that we can do that. Okay, the typical answer now Google will be, why you're stupid, you're silly guy, because you're looking for critical values. I can give you a p-value, but for the moment, imagine that we don't know, we are in the first 90s as your professor of econometrics, so the p-value is something that's very difficult to compute. The table, let me, this is a table of the student t. Okay. Okay, can you see that? Look at this. Student t distribution. This is a typical table of my published on the book I studied econometrics, for instance. So V is the number of degree of freedom. You're seeing that the student t, you need one parameter, which is number of degree of freedom. So our example, I had 7 degrees of freedom, okay? And I have, say, some quantities, this will be T95. So I'm looking for the 95 percentile of the student t distribution with 7 degrees of freedom is equal to 2.365, which is the number exactly, which corresponds, fortunately, it corresponds to the number I put here, okay? What is this number? It's simply, it is written in the slide. The slide said, okay, observe that this number, this mysterious number, is not mysterious, simply are the 95% percentiles, 97.5 percentiles of the student t distribution with 7 degrees of freedom. Which means that if you have a random variable w, which is distributed as a student t with 7 degrees of freedom, then the probability of that the student t is larger than 2.36 and is less than minus 2.36 is 25% plus 2.5%, that is 5%. So the critical value of the test is simply a quantile of a distribution. Stop. And you decide which is that quantile, because the quantile depends on the probability you decide to have on the tails. With 5%, I have decided on the right tail, the probability in the right tail is 2.5%, and the probability on the left tail is 2.5%. So the sum of the two is 5%. You understand that if I prefix the test at a 10% level, not to 5%, but 10%, what I have to do is, I come back here and say, okay, this is the student t, you probably don't see very well, but it's student t with 7 degrees of freedom, the 90 quantile is equal to 1.89. So in that case, if I'm running the test at the 10% level, the critical value will no longer be 2.36, but it will be 1.89. Now I show you an example with Gretel, okay? So don't worry about that. So just let me say a few words about the significant level, then we move to Gretel. So I'll try to resolve you, to have you not to worry too much. So what is this alpha? It's a crucial ingredient of a decision rule. It determines the value which is the cutoff, the threshold of the test. And alpha, we call alpha significant level, or also type 1 error of the test. It is a tolerance level of the test that we prefix. Why? I'll show you why. The typical values of alpha in applied work are 5%, 10%, or 1%. But most of the time, people have in mind 5%. Why? I don't know why. It's a convention. And some statisticians, economists recently have been questioning this convention. But that's not important for it. What is the meaning of the significant level? And that is the point. What is this alpha? Alpha is the probability of rejecting the null when the null is true. So that's why is a probability of an error. And this is the type of an error is the probability that I reject the null when the null is true. It is the prefixed probability of a false rejection, because I'm rejecting something which is true in the population. And let me give you this interpretation. Let me consider this example, then we move to the data. Imagine that I apply a test for COVID on 100 randomly chosen individuals, okay? Something which has been happening constantly in the last couple of years, okay, in world hospitals in the world, okay? I'm just focusing on 100 individuals to simplify. Okay? Suppose that the null is negative, okay? The null is negative, what we want to be. When I had my quick surgery on Monday morning, the first thing they did to me was COVID test. I was praising, oh, I hope I'm negative, otherwise it will be, okay? So the null, I'm negative, so if I prefix to 5%, it means that I tolerate that 5 negative people out of 100 can be false positive. It's a tolerance level. I want to prefix. Imagine, let me give you another example. Imagine that you're doing, say, a trial. The null is the guy is innocent, okay? You know, in Italy, the null hypothesis that you are innocent until it is proved that you are not innocent, okay? So the null is that the guy is innocent. And by fixing to 5%, we are tolerating that 5 innocent people out of 100 can be falsely put in jail. You understand? It's a cost. It's the probability of an error. You could say, okay, what happens if the null is that, say, the guy is guilty? Everything changes, of course. So we focus on what we want to do with our test is that we want to, we put a cutoff, a tolerance level on the null hypothesis, which is the one we have in mind. Okay? So we recognize that because we take a decision in the presence of uncertainty, our test may make mistake, but we want to keep the probability of false rejections, because recall, alpha is the probability of rejected null when the null is true. So it's the probability of false rejection, and we want to control that probability. We want to keep it under control. You could say say, Prof, but I could focus on, this is type 1 error. What is type 2 error? Could be, I could control the probability of rejecting the alternative when the alternative is true. You can do that. Everything changes, but we conventionally focus on the null, H naught. Okay? And let me see what we have. So again, and then we move to the data. Assume again that we are in this example. It's just an example. The student T with 7 degrees of freedom. Okay, the T ratio as a student T with 7 degrees of freedom. You know that under the null hypothesis. So the hypothesis was the Trump hypothesis. The Trump hypothesis was real economic activity has no impact on CO2 emission. Okay. So under the null, the T ratio is student T distributed. So in principle, it can take any possible value. The student T goes from minus infinity to plus infinity, but probabilities are different. Under the bell of the student T, please recall, it's very similar to the normal, but in the student T, you have more weight, more probability in the tails, okay, of the distribution. So rare events are more likely to occur relative to the normal, okay? So, in principle, I can get very large numbers in the right tails, very low numbers on the left tail, but of course, the probability of getting very large and very low, it's very different getting values which are close to 0, for instance, where I have the probability mass is more concentrated, okay? So our point is that the values of the test statistics that occur in the tails are less likely to occur relative to values which are near the mean of the distribution, which is 0. So think about T ratio. When I say the T ratio is the ratio between the estimated coefficient over its variability, if it is large, we are in the tail. If it is small, we are close to, if we are close to 0, we are in the middle of the distribution. Okay? And, okay, let me see. Okay, then we'll move decision rule based on the p-value of the test, but for the moment, we stop here. We make a 10-minute break, and I promise we start with Gretel. We are going to move again to up to this point. We know the student T, but you could say, Professor, but you started with this very general. You have to give me time. It's right. We started from this very general formulation. The student T is a special case of this. Okay. Now I'm just focusing on the student T, but then we'll come back to the very general setup we are studying. Okay. So we take 10-minute break, and then I start.
Scusi, professore, avrei un'altra domanda. Posso anche farla in inglese in realtà, così magari.
Yeah, you better switch in English, please.
Okay. We said that usually we consider a level of significance on 5%,
yeah.
But we also said that we can consider 10% or 2%, right?
1%.
1%, sorry.
1%
could you explain us when it's better to choose a level of significance of 10% or 1%?
Yeah. Okay, I try, but there is not a clear answer to your point, unfortunately. But let me give you just the intuition. So if you have in your special example, your test statistic is distributed like a student T with 3 degrees of freedom, okay? And if you're testing, if the significant, you prefix the significant level to 5%, it means that basically all the value of the T ratio, which are, say, larger than 3.18, imply a rejection, or larger in the right tail, but also in the left tail. So larger in absolute value implies rejection. But if you get values which are inside here, this is the one I'm touching with my hand. This is the acceptance region, okay? Because if you get, for instance, the T ratio equal to 1.8, which is here, you accept the null, okay? If you get 4, where I have the hand now, you reject. Is that clear that this is the acceptance region, this one, while this and these are the rejection region. Is that clear?
Yes, it is.
Yeah. Now, imagine that I want to switch from 5% to 10%. So you should understand that I'm moving this critical value around here. It could be, so here and here, of course, because the distribution is symmetric. So imagine that with the critical value at the 10% will be 2, okay, and minus 2. So what you're doing, you are restricting the acceptance region. So in a sense, you are more prone to reject your null with 10%, because you are restricting, say, the acceptance region. And why should I do that? It is very, the answer to your point is very problem specific. The problem you have in mind. If you don't want to reject your null, for instance, if you believe very much in your null, one trick could be setting 1%, which is you are enlarging. The critical level in that case would be, for instance, 4 and minus 4. So you are enlarging the acceptance area of the null, and you are restricting the rejection area. So it depends very much on how much you believe or not on your null hypothesis. So 5% is a kind of compromise. I can tolerate that 5 innocent people out of 100 can be erroneously put in jail. It's a kind of cost evaluation. In this case, it would be a social cost evaluation that you make. Imagine that we must say, okay, it's an important thing. Being innocent or guilty is a very important thing. So I can tolerate that only, say, 1 out of 100 can be erroneously put in jail. So in that case, you are enlarging. You believe very much in the innocent of the people. Did I address more or less?
Perfect. Thank you. I understand.
There is no clear answer to this question. It's more a convention.
So
yeah.
Can we say that if we select lower level of significance, we are doing a strong test?
Yeah, well, not strong test. We are giving more chance a priori to the null. We give more, but a priori, which means that I'm reluctant to reject it. So 5% is a compromise between 1 and 10, kind of. You might say, why in the fiscal literature they say 52%? Because they wanted. In that case, you want to be in the tails of the distribution. You want to be in the tails. You want to reject your null in that case.
But if you accept it, you're very sure that.
Yeah, if your set is correct, your point is correct, and you will fully understand it when we are moving to the p-value. When we move to the p-value, which is simply the counterpart of what we are doing with the critical value. Okay, it will be the same thing. But right, the answer is yes. So we start around, say, we take at 5:15. Okay, so yeah, 5:15. Yes.
Domanda generale, perché dopo devo prendere il treno. Per gioco finiamo, così decido se magari andare via adesso e guardarmi la casa.
No, non ho capito.
Per gioco finisce la lezione.
Io cerco di finire al massimo alle 6:10 vorrei finire.
Grazie mille.
Okay, guys. So we finish little bit.
Oh, 42. 42. Churchill, Roosevelt.
Okay, so let me come back. You probably recall that we did a wonderful example, I would say, when we want to model. Let me open the script. So what we did in our last empirical exercise, we did, we have a model, we estimated, say, an environmental Kuznets curve on a group of on a sample of 11,700 blah blah households, and the model was we modeled, say, the log of CO2 emission across these Italian households. Those are actual data, okay? We regress on a constant on the log of expenditure or household expenditure, which is a measure of a proxy of the household income, okay? And now we said, okay, in this model we find heteroscedasticity, but we saw that we could address the heteroscedasticity by transforming the variable. And we said, in particular, we defined a new regressor y star given by the ratio between log CO2 over log expenditure, and the regressor x star was 1 over. So you have the slides on that. I don't want to come back on that. Simply, what we did was re-estimating the transformer model, where we saw that we captured the heteroscedasticity of our data. Okay. So I run this code. I want to show you simply the estimation output. Ok. Non so come ingrandire qui. Okay, I can do it by hands like this. Probably you should see. No, okay. Okay, tools, preferences, font scale. I put it 20. I do it by hand now. Okay. Is it okay now? So the regression model is this. I'm regressing, say, the y star, which was the ratio between. Look at here. Y star is the ratio between the log of CO2 expenditure over the log of CO2 emissions over the log of expenditure over, say, x star, which is 1 over log expenditure. So I have a constant, and I'll put x star. We already did this exercise together, okay? I sent you, you also have the PDF, okay? And so by estimating this model, we get the following estimation output, where please recall that since it is a transformer model, the coefficient will capture the impact of, say, the proxy of income over CO2 emission is the constant in this transformer model, which is estimated 0.62. Please recall that if you test now heteroscedasticity, if you run the Y test, you can see that even, okay, let's follow for the moment the rule, the mechanical rule. The rule is that the null hypothesis is heteroscedasticity not present, so homoscedasticity. And you can see that for the moment we have a test statistic. We say ingredient A was null hypothesis and alternative. In this case, the null is homoscedasticity versus heteroscedasticity. Ingredient number B, test statistic. And then we are discussing the decision rule. And for the moment, we are to the decision rule based on critical value. But as I told you, the decision rule provided by any package will be based on the p-value. And we have to still discuss it. But for the moment, please believe me that if this p-value is larger than 5%, 5% is the significant levels we have been discussing. So in this case, I don't reject, since the p-value is larger than 5%, but we'll see the second rule on the slide seriously, so don't panic. So in this case, we don't reject the null hypothesis that of homoscedasticity, okay? Now, let me come back on the estimated parameters. And the parameter of interest in this transformer model, I sent you the slide. I mean, it's just probably you are tired as I am, but I want to show you very quickly. Let me go here. It's material that I already sent you. You already have it. Katzeneth card, this one. Okay. Do you remember this model? We said, okay, we have 11,000. We have, say, 11,748 Italian households, cross-section data. We have this model, the one we already seen, okay? And we have in mind this linear approximation of the Katzeneth curve, but we know we have the suspect that we have heteroscedasticity, so we said, okay, we can do the following. We can move like this. I divided both sides of the equation by 1 over standard deviation. Then we said, okay, let's make the assumption that the variance, the heteroscedasticity, depends on the log of household income, okay? So H, where H is a positive constant time the log. Given this assumption, we rewrite this model in this way, okay? And this is what I've done on Gretel, okay? Now you understand that beta 2 parameter, which is the intercept in this transformer model, is the parameter we capture. Let me go back. Beta 2 is the one we capture, say, the impact of income on expenditure. So beta 2, quantifying beta 2 is very important if I'm thinking about, say, a carbon tax, for instance. If I want to decide whether putting a tax on whether, say, putting a tax which reduces income, household income, I have some effect, some positive effect on, I have a reduction in CO2 emission. Okay, so it's very important to quantify this beta 2. And according to our estimates, the beta 2 parameter, it's, where is it now? It's a model. Okay, the estimated beta 2 is 0.61, okay? Imagine that now my null hypothesis, the one I want to test, given my knowledge, is that, and for the moment, I don't want to look, I don't know anything about p-value, I just know mechanical rules. But I want to test that this number, first of all, I want to test whether the Trump hypothesis is satisfied or not. Now, so I want to test the following null, that this coefficient, the population coefficient, let me call beta 2, is equal to 0, against the alternative that say that this coefficient is different from 0. Because if we accept the null, of course, no way you can tax. Taxing will be simply an externality. There is no benefit. Taxing, say, households will not give any benefit in CO2 reduction. Okay? So we are interested in, first of all, in testing whether beta 2 is equal to 0. And, okay, how large is n is in our setup? We are not in a small sample now. N is large. Okay, so I can assume that n goes to infinity. And if I have in mind the theory, the property of the OLS estimator, I know that in this setup, regardless of the distribution of the error term, the OLS estimator is normal distributed. Okay, it's our previous class. Okay, now, so in that case, I can prove that the T ratio, which is given by the ratio 0.62 over 0.01, the T ratio in that case is distributed if the null that the coefficient is equal to 0, that beta 2 is equal to 0, it will be a normal 0, 1. Okay? Can be approximated by a normal 0, 1. Let me say one thing. If you have a student T where the number of degree of freedom go to infinity, with a large number of degree of freedom, the student T collapses to the normal. It becomes very, very similar to the normal. So, if I want to test the null hypothesis that this coefficient is equal to 0 in the population, I simply take this ratio. And what I have to do now? I have to, this is my, so my test statistic, the T ratio, which is my test statistic, in this setup, large sample setup, is distributed under the null as a normal 0, 1. So, in my sample, I get 50.48. Let me go on the normal distribution. So I can, I should have also the graph of the normal somewhere, but you know it. Okay, this is the normal. And so recall that our number was, our T ratio was 50 point something, okay? Now, from the normal, I know that, say, if I have, if I fix the significant level to 5%, 0.05, so the critical value, the CV95 are 1.96 and minus 1.96, okay? Which means that this area plus this area is equal to 5%. So I have our T ratio statistic is 55 point something. So we are in this tail here, okay? We are here. So according to the rule we have with the critical value, we strongly reject the null. We are in the rejection area. We are in the tail here. So we strongly reject the null that the beta 2 parameters is equal to 0 in the population, as expected, of course, which means, okay, so we can probably tax these people. If we put a carbon tax, we have some chance of reduction of CO2 emission in the among these 11,000 blah 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 households. Okay, so basically, I'm not looking. Let me come back on this. What I've done was a very simple exercise. I'm not looking for the moment to this column here, p-value. I'm simply take the test statistic and I'm applying the decision rule based on the critical value. And what is the critical value now? That's why I have to know that the less estimator in large sample is normal. The T ratio, the ratio between the estimated coefficient over its variability, will be normal 0, 1 in large sample. And then at that point, if the T ratio is 15.48, it is larger in absolute value than 1.96, so I reject the null hypothesis that the coefficient in the population is equal to 0. Just to check whether we understand, imagine that I want to test, okay, the population value, this coefficient, actually we have estimated it to be 0.62, but the population value is 0.70, 0.7, okay? So I want to test the null, let me write it. Where is the word? Oh, let me again. No, I want to do that like this. I do close. Let me stay here. I want to test now that this coefficient in the population is equal to 0.7. I show you how you can do that in Gretel. So under test, you have many options. Among the many options, you have linear restrictions, which is our, which allows to address our general setup, the one we have been discussing today and the one we'll be discussing next week. when we are recovering in our next classes. So linear restriction, I want to test, according to the notation used by Gretel, the first coefficient is beta 1, so B1. We are concerned with the first coefficient. Please notice that it is the constant in the transformer model. Just I want to stress that we have been transforming the model. So we had the beta 2 coefficient in the transformer model is the constant, okay? It was actually the elasticity of CO2 emission with respect to income in the original model. After dealing for heteroscale elasticity, we have this model here. And now I want to test that this coefficient, the beta 2 coefficient in the population is equal to 0.7, okay? Which means that a 1% increase in household income implies a 0.7% increase in the CO2 emission, okay? And given that number, I say that, okay, if we reduce, so if we put a tax with reduces income of 1%, there will be a reduction of CO2 emission of, an average reduction of CO2 emission of 0.7%, okay? Now, let me come back here. No, not here. Okay, what I'm testing now is that the beta 1, so what I did like this, I did test, linear restriction, and now I say the beta 1 coefficient is equal to 0.7, so I write like this. It should, I mean, this is the notation preferred by Gretel, but it's a very simple thing. I click OK, and again, what I do now, again, you can see that Gretel give us the rule based on the p-value that we still have to discuss, but I want to stick now to the rule based on the critical value. Now, okay, imagine that I tell you that under this null hypothesis, our test is distributed by a chi-square distribution with 1 degree of freedom. You might say, well, professor, but Gretel is providing us with an F, not a chi-square. Okay, the theory distribution says that if you have a large degree of freedom in the, say, denominator, since I can approximate this 11,747 people can be kind of infinite, an F1 will be a chi-square 1. Okay, so I have basically under the null, if this is true, my test statistic is distributed as a chi-square distribution, and the value I get in my sample is almost 53. Let's go on the chi-square distribution to see how we behave. Of course, we are running the test at the 5% level. So I go, let me open the chi-square, which is here also. Chi-square. Okay. You can see one feature of the chi-square distribution is that, say, the density, it takes only positive value. For instance, if you have a chi-square with 2 degrees of freedom, the density is like this. And for instance, the critical value, the value such that this probability here is equal to 5%, is 5.99. Okay, this is the critical value at the 5% level if you have a chi-square with 2 degrees of freedom. That is the probability that this W is larger than 5.99 is 5%, or if you prefer, the probability that W is less than 5.99 is equal to 95%, which means the white area inside this curve is 95, and the one colored here is 5%. Okay, you know that the probability inside this curve is equal to 1. Okay, the integral is equal to 1, and so the integral from 0 up to this point is 95. The integral from this point until plus infinity is 5%. Okay, probability are simply integrals of this distribution. Now, okay, in this case, in this example, I have chi-square with 2 degrees of freedom. In our exercise, I have chi-square with 1 degree of freedom. I remember that for some strange reason. If you have a chi-square with 1, the critical value is 3.8, okay? So what I have to do, coming back to our example, our test, which was this one, okay? So our test statistic is 52. The critical value at the 5% is 3. So the value of the test statistic is much larger than the critical value. So we reject the null hypothesis I have here, according to the decision rule C1. Of course, I will stop here because we are all tired. In our next class, I have to finish, to complete our, theory, and we'll, in that case, we also cover this part here, and we don't need to know the critical values from the chi-square, from the student t, we simply have to look at the p-value, okay? But why I am bothering you with this, because you have to know what's behind. Otherwise, you follow the mechanical rule. Okay, if you look at the p-value is smaller than 5%, you reject. If larger than 5%, you accept. That is the mechanical rule. Now you must have the story behind that. You have to be conscious of what is going there. So basically, according to our data, we strongly reject the assumption that the coefficient is 0.7. Is it 0.5? Can I test for given? Let me come back again on the estimate. No, not this one. Where is it? Okay. Maybe it is 0.60 in the population. Let me test that again. Test linear restriction. Where is it? Linear restriction. So let me say I want to test that in the population it is 0.60. And now look at this. The value of the test statistic is less than, in absolute value, is less than the critical value. So we accept the null hypothesis. Or if you prefer, we don't reject the null hypothesis that the population value of the beta-2 coefficient is 0.7. So, which means, from a technical point of view, that if we tax these people and to get a reduction of 1% of the income, we can expect a 0.7% decline in CO2 emission. I don't know. I'm not expert of this issue. I don't know whether it's good or not. Probably not. I don't know. Okay. But it's just to show you how I interpret things. But I will come back on that in our next class when we are fresh. So don't worry. Let me close with the p-value that says decision rule based on the p-value of the test. What is the p-value? Let me give you just a definition. The p-value, so imagine that in my, okay, we can stop here. We can stop here. We start in our next class when we are fresh. We stop here. Thank you very much for your attention, guys.